invited me to this very wonderful conference. This is probably the most physics conference that I have ever attended. I don't. I have all my degree from electrical engineering, so I have very little background on physics. So today we are going to switch gears. So from many-body physics to intersection between quantum chemistry and quantum computation. So this is all this talk is about. So this is still an ongoing project. It hasn't been put up on arXiv yet. We hope that the paper could be released in the next month. And this is a collaboration between Foxconn Research or Hong Hai Research Institute and the City University in Hong Kong. So the first author, Kevin, is a postdoc with Alice Hu in City University of Hong Kong. Their background is like material science, but they recently very interested in combining quantum computation technique into their domain. And Kevin would join my group in July. And today, is there a pointer or the stick? Yeah. So that's the stick. While you and then Yoten is the person who is in charge of quantum simulation in my teams. So yeah. Okay. Before I formally start to introduce the scientific part, I got asked a lot what Foxconn research is doing and what is it about. So I think it would be good to kind of increase the slide to show you what we are doing. Foxconn research started in the beginning of 2021. So this is the 5th years of our group of the whole research, the Quantum Computing Research Center. In the center, we are a series teams. But we want to broadly cover like a good spectrum of quantum computation. So you can see that we focus on 3 large regimes. The first one is hardware enabling technologies. By that I mean that anything related to tells you like the qualities of your hardware or like improving your hardware design. So you can see that includes, but not limited to like error correction, state tomography algorithms, randomized benchmarkings, all kinds of error estimation technique, and even fault-tolerant quantum computations. And then there's a second large part is on software. So in these regions, we are working on algorithms, all kinds of algorithms, query type of algorithms, quantum walk type of algorithms, also with corresponding lower bounds from either classical. The goal is to show quantum advantage with a provable way. We also put efforts on more theoretical stuff, for example, like computational complexity, circuit complexity, etc. So we have people working on circuit complexity, and we are hiring people to work on computational complexities. The last part is like applications, because right now I'm on the evil side of the research. So we need to identify why quantum computation is useful. So we identify a few topics, like simulations is one that's related to what I'm going to talk about today. And then sensing metrologies, and I also put cryptos, and because recently there are a lot of very interesting results from quantum crypto research. So we also have a small teams working on quantum cryptos. Yes. We have a hardware teams within our research institute, and they are working on trap ions, but we are kind of like independent. I do not, I'm only leading this research institute. Yeah. Good. So our team is still expanding, and we have very flexible working styles. So, for example, half of the teams, like myself, even though the position is in Taipei, I live in Australia, Sydney, and working remotely for the companies. We have people in right now from Kyoto, Japan, and two people in Hong Kong. These two collaborators of this paper now is in Hong Kong. Two members in Sydney, Australia. So if you any Korean student wanna stay in Korea but still want to work on the theory side of research, let me know. Okay, now let's start it. This work is about simulation of materials, and in particular, we want to explore possibilities of simulation of material using quantum device or quantum computation. And I mean, this is the goal of simulations, right? You have a physical systems, and you want to identify, like, I think in the restricted sense is to identify the ground energy and the ground state so that you understand what is the stable systems. And this is kind of like the chemistry Hamiltonian, given molecules and ions and their relative mass and the distance, then you can write down the Hamiltonian. But because the system is very complicated, they have a lot of electrons, a lot of ions, and so it's difficult to compute their ground state and ground energies. So so the first step that this quantum chemists do is to do some approximations, and this one is Weir-Gnomes, Born-Oppenheimer approximations. So basically, because the ion has much greater mass compared to electron, so you can consider that as the classical terms. And then, so you can remove any like those five terms that have only the ions. Just keep the terms with electrons. So you have like ion electron. So this is like Coulomb interactions. Okay, and so this is basically what we started. So this kind of more approximate or simplified Hamiltonian. Okay. So the first step that the chemistry did is that because the wave function is very complicated and it's infinite dimension, so you basically want to discretize it. So you use some basic set to discretize your wave functions, and there are two families of this basic set. The first one is called molecular orbital basis, and the second one is called the plane wave basis. I highlighted what you focus. So for molecular orbitals, it's more compact way to describe molecular systems. And normally, so the M here is the size of your basic set. And in this case, M is normally much smaller compared to the plane wave basis. And the plane wave basis is basically used to describe solid state with periodic boundary conditions. So these are the main the difference. So normally in the plane wave basic set, you would have a much larger M. So their basic size is much larger than the molecular basic set. Okay, you can ignore all the remaining. Just remember that plane wave is for periodic systems. Molecular basics is for molecule systems, and the basic size for molecular basic set is smaller. M is much smaller, but the plane wave has a much larger M. Then, like in 19 1920s, I think I don't know whether it's physicists or chemists. They started to use these first quantizations to kind of like describe a more complicated like n-body wave function. So basically, you could describe n-body wave functions from single body wave functions by using this they call Hetrick product. But if you look at this, if you exchange the I electrons with J electrons, this does not respect or obey the Pauli exclusion principle. So if you just exchange these two electrons positions, then you don't have this phase. So in order to make it a meaningful wave function for n particles, you would have to include all the linear superpositions of the terms with phase. So, the first quantizations with Hetrick product representations require a lot of storage space. So you basically require n factor space to store all your wave function, n particle wave functions. And then around 1940s, 43, then they have this notion of second quantization because people noticed that you could arrange this n particle wave function using the so-called Slater determinant. And because it's a determinant, if you change two positions, that's equivalent to change the corresponding two rows, and then the phase would naturally show up with this Slater determinant. And that's why after second quantization, after Slater determinant is introduced, all the quantum chemist people normally exclusively use second quantization in their research. When I say quantum simulation, these are classical computations, classical quantum chemistry. Okay, good. So with the corresponding this wave function representation, then you could also kind of like rewrite your Hamiltonian with respect to those wave functions. For the first quantization, the wave function has a nice simpler form. So this is like K product notations. But for the second quantizations, then this Fermiani operator, creation and annihilation operators would show up. And you could see that here, these four-body interaction terms, and you like the overall, the sum of those terms is equal to n squared m to the power 4. But this is just a basic stuff. But for specific representation, of course, that you could reduce the representation further so that you could, for example, in this second quantization, in recent research, you could bring the number of terms from the fourth order, like m to the power 4 to m to the power 3 for specific molecules. And similarly, you could kind of like massage this representation in the first quantization. But this is not extremely important for our talk. Okay, and then these are the four most well-known approaches in quantum chemistry regimes to do classical simulation of materials. From the left, these are the most easier ones. So Hetrick-Fock approach, and then density function series. I'm sure that many of you have heard about this density functional series. These two approaches has very low accuracies in terms of the energies that you estimated. But the advantage of this approach is that their complexity is relatively low. So n is the number of electrons. So you can see that like the reason why DFT dominate the classical simulation is that it really is the most efficient classical algorithms. And also because they did make a lot of assumptions, they make a lot of approximation and simplifications in their optimization questions. So that's why the storage of the classical memory is also fairly mild, right? So M is the size of the basics that you choose, N is the electron number. So, still like DFT is still a very popular research area. And then in the middle region, it's called this couple cluster single and double simulations. In this case, you kind of like expand your the search space of your wave function to include double interactions. So in this case, that the storage goes from linear to quadratic, and then it also increase your time complexities. And remember that if M is normally, for example, if it's in the plane wave basics, M is much larger than N. So you see like these two approach that's mostly more exclusive for molecular basics, because if you use plane wave basics, M would blow up. Finally, like the full configuration interaction provide you the most accurate outcomes, but unfortunately, either the storage or time complexity is kind of like impossible to handle even for our supercomputers. They all have this exponential blow up in terms of storage and time complexities. So this bring opportunities to quantum computation, and I think this is why people in our communities think like simulation would be like one killer application of quantum computations. So so this is actually what we are at right now. So for the single electron systems, we could have analytic solutions, so we know this fairly well. But then once we go outside of single electrons, then we could only get some approximate solutions. And in the like material science, they really want to understand those more complicated system betas like high TCS, right? But again, because if you want to do like very accurate like FCI simulations, that you normally run out of computation powers, even with the most powerful superconductor on Earth. So we could only have very limited result, and also for very limited situations. Okay. Now you could really see that why quantum simulation is attracting a lot of attentions. So these are the classical approaches: H3Fog, DFT, CCSD, and FCI, and these two are the quantum simulation result. So both of these two papers comes from Google Quantum AI teams, but collaborating with for example, Nathan Wiebels and people's students from Harvard and MIT. You could see that let's ignore this detail, but if you just look at the time complexity, right? They can achieve very high accuracy, literally chemical accuracies. But if you look at their time complexity, this is literally exponential speed up in terms of the circuit depths. Also, and I think this is because in the quantum regime, you can encode the states in superposition. So that's why the number of qubits that you need to use in the quantum simulation is very mild. But of course, like what I'm saying here is fully tolerant regimes. I will show you some resource estimation count that the circuit would require like 10 to the power of like 15. Uh, uh,
Accuracy high versus low.
so high means that they can achieve chemical accuracies, and low is like this is way far away from chemical accuracies. For the chemistry people, they care whether they can obtain the ground state energy within this how to call it, is 1 bar or yeah, 1 million Hachi, yes. So this is within this gap between the real ground state energies.
Oh, so is there any reason why EFT has a low accuracy? Is it like fundamental limit?
Yes, because basically these are all optimization questions. So you choose your basic set, then you form you from this basic set you form your wave function, and for the DFT or for H3 your wave function is restricted to one Slater term. So this is very small search space. And it's likely that the true wave function is far from this. But because you limited your search function, like the search space, then your ground state energy will be kind of like away.
So is this an empirical accuracy, or is there a rigorous bound that it has to be low?
No, not. It really depends on situations. So, like I said, if you go back to, there are certain situations you probably the final ground state energies is probably would match the search space that started with DFT, and that in that case you could get good approximations using DFT series. Yeah, but not for the most cases. Only for very special situations. Okay. Okay. So these two papers kind of like the starting point of our research. So we are reading the papers, and we find that very exciting, and we are looking for problems that we can further build upon this result. So when we read that papers, it's pretty good, right? So we know that n log m is kind of like optima. So you could kind of like represent the most complicated wave functions use like it's m to the power of n possible state, right? So and this is why you need n log m qubit to represent all those wave functions. The TOEFL cost is also reasonable. It's a nice trade-off between number of electrons and the size of your basic. So this is still the base scaling of today's. But then this result is kind of like counterintuitive, because I mentioned that in quantum chemistry, all the classical approach, they stay in the second quantization instead of first quantization, because first quantization has a very strict limit, is that it only represents the particle conserving subspace. So for example, you started with n electrons subspace, then the whole computation has to be in this n electron subspace. But then I will give you examples that in many cases that there are creation operations and annihilation operations that will bring n electrons to n plus 1, n minus 1, and then and this first quantization won't support that kind of operation. So this is a very strong limitations of this approach. And also, secondly, in the paper only strictly work for plane wave basics instead of molecular basics. So it would be good like if we could also change the basics in this first quantization representations. Okay, and this second paper was also from Google, but in that case, their qubit count is m, but remember that m normally is much larger than n, the number of electrons. So you normally need to have a basic set with a lot of elements in it. So this seems not optimal in our case. If you also recall that in the first quantization, the qubit cost is n log m. That is optimal. But this should be fine. Like if you are working on molecular basis, because in that case, like n roughly equal m. So again, when we read it, we identify like there's possibility to improve the qubit count. So we also look into how to properly improve this second quantization simulations. Okay, so let me then show you why, even though these two quantum simulation results from Google AI teams are quite interesting, but they cannot be applied in kind of like a broader sense. So for example, if you look at the green functions, I don't have much backgrounds on green functions, so this is basically provided by my collaborators. This is a quantities that will tell you kind of like, for example, optical spectral informations, references here, and it also tells you about properties of particle excitations like excitons and phonons. And then it also allows you to study reaction dynamics. So take the most simple form of these green functions. So this is called one particle green functions. This is the formulas that you want to compute, right? Given a ground state and this is your observables. And notice that they this creation and annihilation operators followed by kind of like a inverse functions, a matrix. So in the first quantization, you won't be able to perform this kind of operations in your quantum computers. So so like I said, if you want to compute these green functions, you are forced to use the second quantizations. But then these Google papers kind of like tells us that the state preparations and this inverse by quantum SVT, single value transformation algorithms, these are more efficiently conducted using first quantization. So these are the complexities to implement. So qubitization is used to implement to prepare this state. And this is implemented by QSVT, and you can see that first quantization is more efficient than second quantizations. So so I think this would kind of like already bring up our results. So we want to bridge this gap so that we created a framework that you could switch between first quantization and second quantizations. That's another examples. I would have more examples after I introduce our result. So in this reduced density function, reduced density matrix, for example, if you take derivative of your eigenenergies, like the first derivative would tell you like information about force. The second derivative would tell you about information on like frequencies. And if you take the derivative with respect to the eigenenergies, then this kind of the reduced density matrix will show up. So this is called a 1 RDM. This is called the second 2 RDM terms, and there's also like higher order RDM. So depending on how many terms you have, and in this case, this also has been known and computed. So this paper, this is from our communities. They use first quantization. The reason that you can use first quantization is that you can start. Sorry. You can start with the first quantization Hamiltonian, and then instead of creation and annihilation, this will become a bracket. So you could also start with the first quantization Hamiltonian. And then if you start with the first quantization Hamiltonian, then this paper tells you that this is roughly the time complexities that you require to compute this density using quantum simulation approaches. And you see that this is log m at n to the power of k. K is the number of observable that you will measure. So it's and that's a corresponding result on second quantization. If you look at the formulas, right? So this works if m is much larger m, right? Because this is log m right here. And in these formulas, this second quantization, it works much better if you are in the molecular basics or molecular situations. You only want to have a small k, right? Because this is to a power of k. If k is small, then it still could be managed. Sorry.
Why do you have k to the k factor?
Yeah. So this is kind of like constant. So you could, I mean, if you fix k, this is, so you can ignore that. Yeah.
Why is it it's not n to the k?
Sorry, n to the k?
Oh, like I guess why do you?
No. Yeah. So this is kind of like a typo. I shouldn't include that. Yeah. Because we treat k as some constant, so it shouldn't appear in that. Yeah. Okay. So this leads to our result. So our result is not super deep. Basically, we identify the difficulties, and we think of way to bridge between the first quantization and second quantization. So the core contribution of our work is that we propose or we designed a conversion circuit between first quantization and second quantization. And for the first quantization, it is this encoding method that used in the Google paper. And then in the second quantization, we use this recent result that's called sorted list encoding. This technology is late in the second part of the paper, but basically we have a conversion circuit, and the cost of the conversions between these two quantizations is kind of like very mild. So it won't introduce further complexities to the quantum simulation. And then the second result is basically to provide a better analysis of this idea. So this idea, they only provide to encode the different basics into a quantum state, but they do not provide further analysis. For example, they do not talk about how to perform totalization steps or qubitization step based on this encoding. And if you could analyze this totalization step or qubitization step, then you could construct a quantum phase estimation, and then you could further do quantum simulation explicitly using this sorted list encoding. So this is our second contribution. Okay, so this is the kind of like the highlights of our first result. So remember that we have a circuit that convert between two encodings in the corresponding quantizations, and the gate cost is n log m. So this is very mild if especially like in the plane wave basics, right? So this is log m. And the cubic cost is n log m. And again, this is the optimal cubic cost. And also normally you don't need to, the times that you have to switch between different quantization is normally constant. So you don't need to like switching back and forth. So overall, you don't, I mean, this is kind of like, you can also ignore this. Okay, so remember that this is the first example I mentioned, right? This is like one particle green state, green functions, and I mentioned that the ground state is more easily prepared using qubitization circuit in the first quantization with plane wave basics, and this step is basically from Lin-Lin's paper. So he has a approach to show you how to use qubitization to prepare this. So then the workflow is, oops, oh, okay, good. So the workflow is that you initialize your circuit in first quantization in plane wave basics, right? And then you use our approach to convert that to the second quantizations. And then in the second quantizations, then you could perform this fermionic approach and act on it. And then you convert it back to the first quantization and use and apply QSVT circuit, and then convert it back to apply this, and then using Hartman test, and then you could get this quantity. So this is the overall workflow. So with our, sorry.
Applies in the ground state?
Yes. Yeah, it's an approximate ground state. It's not the exact ground state. The ground state, so this is basically, I can provide you a reference for it. You could do it using Lin-Lin's approach. I can do that for you later.
But it's not exponentially expensive.
You have if think about the ground state, yes. But normally in the quantum chemistry, you could combine informations from so for example, remember that when I talk about the classical approach like CCSD and FCI, normally the way they identify their basic set is that they take approximated state from Hartree-Fock or DFT, and then they build up a basic set for that. You could also do that in the quantum cases. Yeah. So you are not you have partial information of your ground state, and then you could then construct an approximated ground state from it. Okay. So if you look at the green functions calculations using quantum simulations, these are the best result up to date. Before, so the one is with plane wave basis in the second quantizations, and the way they implemented that inverse matrix. One is using QSVT, and one is using another inversion method. And then this is the corresponding complexities. But if you use our hybrid one, because then the initializations and the inversions can be done much more efficiently in the first quantization, right? Then you could have this much improved scalings. So for example, if you look at this corresponding one, this m to the power 5 could be reduced to m. Like, and we again, I highlight that m is normally much larger than n. So yeah, so this is omega is called a cell volume. So normally in certain situation, you could take omega to be like n, order of n. So then, yeah. And this is the, this omega depends on, it's a cell volume. So it kind of like characterize how big the cell that you want to simulate. Yeah. So normally we take that as n. Yeah. It's called singular value transformation technique. Yeah. Which one? Oh, sorry, not the. So this is like the gate cost. So the number of gates that you need to implement. I apologize for that. Yeah. And then for reduced density, then it gives us flexibility, right? So you could initialize, stay in either first quantization and second quantization, and then depending on the corresponding cost to compute, right? Then you could switch. So this somehow just provide you a more flexibilities in doing quantum simulations. So this is kind of like very my stuff. Then this third application that hasn't been mentioned in the literatures. So we find that this called the ionization probability or attachment probability is given in terms of this. Again, this psi n is like kind of like the number of electrons for your neutral systems, and this n is the small n is the excited state, and capital N is the number of electrons. So these quantities could tell is used to compute the accurate ionization energies. Again, I'm not from material science, so I really do not know much about that. But this is the application that identified by my collaborators. And you could also use these two quantities in computing another versions or a different representation of green functions. And then if you look at how to do that, it's similar to the first application, right? So you initialize that in the first quantizations, and then you switch using our approach, our circuit to convert to the second quantizations, and then apply that, and then go back and then compute these probabilities, right? And this would give you a much more efficient quantum simulation. Okay, the last one is probably the most complicated system, right? So this is kind of like you have you have a suffix, and this is kind of like periodic system, the solid systems, and the ground state is normally easier to describe using plane wave basis. And then there are the different species that you can attach to it, and this different species, because this is more like a single molecules, so they are easier to describe using molecular basics, right? Then if you want to conduct a quantum simulation of this kind of complicated systems, then it involves several steps, right? So you have to first you initialize this suffix in the plane wave basis, and sorry, this is right here. So the surface is initialized in the plane wave basis, and it's very efficient to do it in the first quantization. The absorbed species, because it's more like a small molecule, single molecules, then it's easier to like initialize using second quantization. The second quantization is more efficient if you started with molecular basics. But then you could, we have approach to switch between molecular basis to the plane wave basis in the second quantization, in the first quantization, and then convert to the second quantizations, and then you conduct the tensor product. The reason that yeah, so and then the tensor product is easy to, it's actually necessary to be done in the second quantization, because the first quantizations, then the tensor product would break the anti-symmetries, and that's kind of like from this Pauli exclusion principle, it's not applicable. But then when you want to do the Hamiltonian simulations, then it's more efficient to switch back to the first quantizations, right? So then because of our conversion circuit, then you could literally did those steps in the most efficient way, and also bypass like the first quantization only works for particle preserving subspace. Yeah. So then it kind of like broadened the scope of what quantum simulation can do in the material science. Okay. I probably would skip the proof. So basically, the proof is a kind of like applying a sorting network, and the sorting network. So because you have two encoding methods, one from first quantization, and then the next is the sorted list in the second quantization, and the sorted list encoding, you require that the indices is in ascending order, so that's why you require a sorted network. And this scaling is actually comes from you applying this sorted network. And this sorting network will require this many of gate count. Okay. So the second part, I would like to talk about this sorted list encodings. The sorted list encoding is basically like if you have n is 2, so you have 2 electrons and you have 15 orbitals, you can encode that into 4 qubit, because this is log m is 4. So then you can see that if you have these two, if the electrons occupy these 2 orbitals, then this is their binary representation. So overall, you would need a qubit to represent these wave functions. And the scaling is optimal in terms of qubit count. So this is n log m, because like the overall state is m to the power of n. So if you use superposition, then n log n is optimal. So our second result is really to use this sorted list encoding and design trotization circuit and qubitization circuit for it. So this is what we do. Once you have trotization circuit and qubitization circuit, then you could use either approach to design the quantum phase estimation to read out the ground state energy. And this is like normally the standard way of conducting quantum simulation. And in our case, that we provide like a proper analysis of these trotization steps and qubitization steps. So in the trotization step, it really depends on what kind of product formulas that you use, and you would have different qubit cost, gate cost, and similarly for the qubitizations. I would probably just use the next slide to show that. So for the trotization steps, it require kind of 2 steps. Like you start with second, because we are now extremely using second quantization and sorted list encodings. So this is the Hamiltonians. But the first step is like you want to kind of like convert the Hamiltonian in fermionic more efficient representations. So there are already like known encoding methods like Jordan-Wegener, Bravik-Kitaev, and Perotis, and you could convert like this kind of fermionic operators into Pauli streams. And there are also other encodings like QEE, random linear encoding. This is our paper. And this is the latest one is called the sorted list. And if you focus on this, if you do not did any conversion to a more efficient representation, if you directly started with that, converted to polystream, then this is very inefficient. Yeah. So the first challenge that we face is that we need to have a more efficient representations. So so this is how we kind of like convert these terms to instead of single terms, we pair them into these four, and this forms like a basis, and then each individual will correspond to like unitary terms. And the scaling is also efficient. So it's the final like Hermitian terms. If you rewrite this in terms of this, then it's m to the power 4. So it's efficient. The number of terms did not blow up. Okay. And then once we have the new representation, then the next step is to apply these product formulas to implement these proper trotter steps. So this is like Suzuki trotter. You take the first order approximations. And then there's another random method, just called Q-drift. And then you could like kind of like mismatch. So you could have determinant. I'm less familiar with this part, but you could easily do the analysis with this. So the final cost. So we, of course, that if you look at the series results, so that this is like the cost analysis in terms of NM and the number of terms in your Hamiltonian. But let's make it more explicit. So we did the resource count with respect to the different systems, and the number of circuits that you require to implement this totalization step is still crazy. So that's why I'm saying that this is not a near-term, another near-term NISQ approach. It requires deep circuit in order to get good quantum simulation outcomes.
That is the number of completes?
Yes.
What will be the depth?
I think it's roughly in this order.
That's probably harder than factoring RSA.
Yeah. But this is through totalization. If we use qubitization to implement quantum phase estimation, this is much smaller. So I will show you. How many? I think I'm running out of time. So maybe I will just directly jump to this slide. So this is instead of totalization, you could use qubitization to implement that. And in this case, right? We also have this in the previous slide. So right, but now the gate count is like 10 to the 13 instead of like 20 something. So we sorted this encoding and the qubitization circuit is actually much better than if you do it through Jordan-Wegener. Like if you look at the qubit count, so you have a lot of saving in terms of qubit count. But for the hopefully gate cost, in certain cases, we do gain a little bit. For example, this one, we do gain a little bit. But for this chemical systems, then it's roughly the same. So
this qubit count is a purely representative.
Yes.
But if one has to do like say cultivation or distillation to get total least, I guess the number of actual qubits
they also yeah. I think there is a way to switch hopefully gate count to T count. But again, these are non-Clifford gates. So
This is also assuming all elements are both four.
yes, yes. So yeah, so we need a true quantum computer in order to do this more proper quantum simulation. Yeah, but it shows promising if you look at the asymptotic scalings. Okay, I think that's it. Thank you.
Okay, questions? So maybe I can ask a very nice question. So if you compare the first quantization and second quantization, the second quantization is already anti-symmetrized by the permutation. So it seems like you're losing some information or like compressing to them, but does it matter to the information contained from the one and the other? Or does it doesn't matter because if you once calculate the ground state should be always symmetrized, so it doesn't matter of the loss of information. Can you explain a little bit about that?
I think firstly, in the chemical systems, those Hamiltonian is basically particle preserving. So I don't think if you switch between them, they would lose any kind of information in between.
Yes. So
but for more general system, there might be, yeah. But
yes.
at least for this chemical system,
like a proper ground state that represent the system, then the conversion doesn't matter of losing the information. Okay, thank you. Yeah.
So the gate cost you showed for the trotter, is it for just the first order decompression or like in general any P with large P limit something? Yeah.
Could you repeat your question?
So in the trotter decomposition you use, is that just the first order or second order?
You could choose. So for example, we choose first order here, but then you could use more. So there's second order Trotter Suzuki, and then there's also so even for the random one, that's instead of Q-trip, we also have another paper with Dominic Berry that improve to 4K plus 2. So you could apply different methods into that and then obtain a corresponding gate count. So the formula, it really depends on this one.
Yeah.
So basically there is the exact formula is much more complicated. I highlighted only relevant quantity here. So for example, this lambda will show up, right? Lambda characterize your Hamiltonian terms, and the overall gate count is 1 over lambda if you use Q-trip. So there are complicated terms in it.
Yeah, okay. But another question is that so recently people are devising several techniques to utilize like the symmetry inside of the Suzuki trotter or some other like a time inversion algorithm. So do you expect that such an algorithm can reduce the gate count?
I think so, yeah. Because here our goal is not to optimize through this products formulas, right? So if you're using better product formulas, then it's possible to bring the total cost down. I think the goal here is to provide a framework that you could work on the representation, like either first quantization or second quantization, and also corresponding basics. And then you can really convert between basics in quantizations and also in different quantizations. And then you can choose the most efficient approaches in either one.
So there may be some more room for the optimization. And yeah, my last question is that, so throwing all those optimization, what is the number of gates you expect to achieve? Is it can be like lower than 10 to the 12 for some complex molecules, or it still should be more than like 10 to the 15 something?
Yeah, I think our next step is to provide a refined optimization scheme, because right now it's just this estimation is normally could be off by maybe sometimes they're older because, like I said, they are constants here and there, and we normally just ignore that if we care about asymptotics, right? But you could perform a much more refined analysis in many of the steps. Yeah.
Yeah, thank you.
Is there a simple way to understand why your encoding gives better cost than Jordan-Wigner encoding?
So the Jordan-Wigner is very inefficient in terms of qubit count, because it basically if you have m orbitals, then you have m qubit. But in this sorted list and also in this encoding methods by the Google teams in the first quantization, they use kind of like a superposition state. So they convert, say you have 15 orbitals, then you converted that into binary representation, right? So for example,
Yeah, I think I'm okay with that part, but network, then like you would probably have to pay some to fully there. Whereas like if you just use Jordan-Wigner,
Yeah,
each term seems much simpler.
yeah, right. So something that I skip is that, so for example, in the traumatization steps, so we convert the fermionic operator, this creation annihilation, to marijuana operators. So this is to bypass that cost. Sorry, wrong direction. Yeah, so like if you are big, I mean the idea is probably the same, right? So you don't want to pay this extra penalties if you convert it to poly. So in our case, poly is not the right way to do. So in the qubitization, we switch to the marijuana operators, and they would bring this down to equal to that.
Okay. Yeah,
Thank you.
I'm still concerned with the ground state preparation step.
Okay.
I mean, ground state preparation is in
It's
general
very super hard. Yeah, I know. Yeah.
very hard. So what's the assumption there, and what kind of molecules work?
So I think the result from Lin is that if you know that the gap between the state you are preparing and the ground state you want, so the inner product is say lambda, and this lambda terms will show up in the cost of your preparation steps. We somehow kind of like I cannot remember that how we replace lambda in our formula, but this is basically you have an estimate of that lambda and then put that back to the formula that they have.
Okay, so you want 1/poly overlap with
Yeah.
Okay.
Thank you.
Okay, last question. Okay, maybe I can just have a last short question. So, is it also possible to apply your method for beyond the ground state, like first excited state, or?
I think so. Like this ionization that is go to like unexcited state. So you could literally do that.
Okay.
Yeah.
Thank you. So, okay, then let's thank our speaker again. Yeah. So I think we can restart the next talk at